Okay, today's lesson, integrals as net change, part 2. So just another example of the stuff we were looking at last day. So in the previous lesson, we saw the integral can be useful for solving problems involving motion. We now extend those ideas to other situations. And the big tip of the day is if you want to find the cumulative effect of varying rate of change, integrate it. Hopefully I will make that clear what I mean by the end of this example. So here's another different situation. The rate of turnip consumption in Canada can be modeled by C at t equals 12t plus 4e to the, ooh, that's a negative in there. Lost that in the shuffle there. Negative 0.04t, where t is the number of years since 2000 and c is measured in millions. So we're measuring in millions here, but the other thing is what we're talking about here is how many turnips get eaten over time. So if you want, this is turnips per year that they've got here in millions, yeah? And why I specifically put the unit down there is it really helps me when I'm doing these integral questions to really think about the units going on here, is that we're talking about turnips per year. Eventually, we're going to multiply that by years, and that'll give us turnips. And then once I have those units in my mind, it really helps me to set up the Riemann sums and the definite integrals. And what I mean by that is I don't know exactly what this graph's going to look like. I don't really care. Some kind of graph that indicates how much how many turnips are being consumed each year. And so at any point there, what we're finding is the consumption. How many turnips? So every time we find the height out there, we're finding the consumption. And then when we make a little rectangle around it, or a trapezoid or whatever, every method heads towards the same answer. What we get here is a little time period. And so the height of the rectangle is the millions of turnips per year. The width of the rectangle is years, some small decimal years. And when I multiply those together, each area represents a number of turnips. So when we find the area, we're taking the c at a certain k value at a certain time, and that's what we're saying here is at a certain time, and we're multiplying that by whatever delta t we've chosen to do the question. Usually we send the delta t to 0 inside the mathematics so that the number gets as accurate as we can. And what we're doing is adding those all up. So when we do that, we're talking about a Riemann sum. We're saying, okay, we're going to add up all of these consumption numbers times the little delta t's, and that'll give us a nice area that will represent the amount, the number of turnips. Then when they want it as a definite integral, so then I go, okay, the amount of turnips is going to be the integral from sum a to b of the consumption times the little delta t's times the little dt's. Well, in this case, they gave me the equation, so I can fill that right in here. Integral from a to b, 12t plus 4e to the negative 0.04t. And it asked me to use the definite integral to determine the total amount of turnips that have been eaten from 2000 to 2015. Now, the important thing here is this is years since 2000, so this 2000 here is t equals 0, making this t equals 15 in this equation. So I'm actually going to use the definite integral. That's all I got to do for the rest of this example. So the amount of turnips, I'm integrating from 0 to 15, 12t plus 4e to the negative 0.4t dt. So I need that antiderivative. Well, let's see, 12t would have come out to a t squared. When I multiply that by 2, I guess I need a 6 out there. Oh, this one's tougher. 4 is what's out front there, and it's going to get multiplied by a negative 0.04. Lots of ways to think this out. One way is just to go, okay, well, I need whatever 4 divided by negative 0.04 is, because that's going to get multiplied by the negative 0.04. So I need a negative 0.04 in the denominator to cancel. And I got to evaluate that from 0 to 15. When I type 4 divided by 0.04 into my calculator, I get something that might make a little more sense, which is just the number 100. Maybe you could already see that coming. You got to multiply negative 0.04 times something and get 4. Maybe you see it as 100, but there's multiple ways to come up with that. You just got to play around and get those coefficients to work out right. Okay, so 2 brackets. I got to put the 15 in there. 6 times 15 squared minus 100 times e to the, let's see, negative 0.04 times 15, or negative 0.6. I got to subtract from that. When I put a 0 into this thing, I get 0 there. I don't get 0 in this one, though. E to the 0, which is 1. Oh, it's just negative 100. So we'll go up here. First bracket, let's see, type that in. 1350 minus 100 e to the negative 0.6. I guess I really don't need that bracket now. And then plus 100. It's got that e in there, so I better type that into my calculator, and I get 1,395, rounded off, million. 1,395 million turnips got eaten from 2000 to 2015 there. And, you know, I want to go back to this unit thing just to mention again. When they give you turnips per year, you're just dying to multiply it by years. And that's what the integral is all about, is saying, okay, each y value, if you want, is turnips per year, and each of these little widths, these delta t's, are a number of years, and when you multiply those together, you get turnips. And you got to add up all those pieces to find out the turnips over the whole period of time there. Okay. If you don't have the equation and you're doing it from data, we have some other methods to handle these things. And take a look at this situation. A pump connected to a generator operates at a varying rate depending on how much power is being drawn from the generator to operate other machinery. So apparently we don't get all the water we want all the time. We just get whatever power is available. The rate, gallons per minute. Okay, and my brain's already flashing at this. It's looking at gallons per minute, and I'm going, okay, if I can take the gallons per minute and multiply that by minutes, I'll get the gallons, which is what I'm after here. So I'm already looking at those units and helping me organize in my brain how this is all going to work. How many gallons were pumped during that hour? Well, okay, with data like this, there's lots of ways to handle it, and one way is with the trapezoidal rule. Might be dropping back into the recesses of your memory, but if you turn to page 310 in your textbook, they summarize it again to go through it. And basically what happens is, I'll draw a little diagram here from the textbook here. Basically you've got some kind of graph you're trying to take the area of, and you're going to divide it into little trapezoids. See, the trapezoids work a little bit better because I'm really exaggerating it here, but each trapezoid is going to, pretty closely model the area. The nice thing about trapezoid is it sort of models the rate of change for each section here. And so you got all these little trapezoids. And now, if we're trying to find an area from, say, A to B, then what we're going to do is divide these into little sections here. These little sections will each be h wide. And how do we get the h? Well, you take the b minus a, and you divide it by how many sections you want to divide it up into, and that'll tell you how wide to make each of these little sections. Hopefully this is all starting to ring a bell a little bit. And then when you do that calculation to find the area of all those trapezoids, find the area of the trapezoid has a formula. When you put those formulas in, you end up with this total formula for the trapezoidal rule, h over 2 y0 plus 2y1 plus 2y2 plus 2y3. You got to add 2 of each of those y values, and then finally whatever the last y value is, you only add once. And the reason there's 2 of each one is because every side of these trapezoids is used in 2 different trapezoids. It's used in the left trapezoid, and it's used in the right trapezoid, except the left and the right endpoint, which they only get used once because they don't have a trapezoid on the outside of those. And the diagram on page 310 sort of illustrates that, and you can sort of see the development of this thing. For now, it's just nice to have all of that into one formula like that you can use when you have data like this that's changing over time, but you don't have a formula for every single moment. So when I put all those numbers in, okay, well, I'm going to do my calculation on this one. We got to find this h before I even start here. And so the h in this scenario is, well, okay, first of all, b minus a is just 60 minutes. They went, the whole thing is 60 minutes long, and they divided that into 12 sections. So the h is b minus a over n, which is 60 over 12. The h is 5, and maybe that's like, well, duh, yeah, I know. Look at, there's the h right there. It's 5 every single time. But I just wanted to show that formula, how it's used when you don't have nice numbers or nice gaps here like this one has. Okay, so then I'm ready to use my formula. Total, screen's jumping around there. Total area equals 5 over 2. I calculated that a already. And then now I need a y0, which was 58, plus 2 y1s, which was 60s, plus the next one, which was 65. I'm getting to the point where I can see them on the screen there. Plus 2 64s, plus 2 58s, plus 2 57s, plus 2 55s, plus 2 59s, plus 2 60s, plus another 2 60s, plus 2 63s, plus another 2 63s. Who did I get them all? There's supposed to be 13 pieces of data there. 2, 4, 6, 7, 9, 11, 12, 13. Let me just check them again. 58, 60, 65, 64, 58, 57, 55, 59, 60, 60, 63, 63. That's the real tough part of these questions, is making sure you don't lose focus and you get all those values in there. So I always double check them to look through there. And when you type that all in, I get 3,582.5. Go back to the units here. What were we calculating? We were multiplying gallons per minute times minutes every single time. And so this total that we've added up is all the gallons that got pumped out. Okay, so a little practice on the trapezoidal rule. If the trapezoidal rule is backed into the recess of your memory, like I say, page 310, you can do a read a couple of examples there to make sure you got that all narrowed down and ready to rock and roll. And that's the only example the only two examples for today is one with the trapezoidal rule, and then one with a that wasn't just physics, something reaching out past physics a little bit. All right, work your way through that homework. We're coming to the end. A few more lessons to go here, and have a great day.